Hello everyone, let's talk about fake base station radar and uncovering these fake base stations at scale in the wild. This was originally presented in the Network and the Distributed System Security 2017 and was originally presented by Zhenhua Li, Weiwei Wang, Christopher Wilson, Jian Chen, Chen Xian, Dehu Zhang, Lan Zhang, Kevin Liu, Xiangyang Liu, and Yuanhu Liu. Today we will go over what these fake base stations are, why are they out in the wild, and how can they be detected and be removed. These fake base stations typically are imitating the real base stations for profit and fun. And we'll also next go over some of the current existing state of the art, the current methodologies, and how these solutions are used to detect these fake base stations and also go over their limitations and their effectiveness. And then we would go over the proposed system in this paper, which uses the crowdsourcing data from users, and that will be used and how they are being used to detect and locate these fake base stations. And later we will look over how 5 key methods as a part of this proposed system are used to detect and uncover these fake base stations. And finally, we'll summarize on the performance of this proposed systems in comparison to existing systems and also their performance metrics in the real world. As you may know, base stations constitute the basic infrastructure of today's cellular networks. Cellular technologies have grown multifold in the last 2 decades, and with the advent of new evolving 4G, 5G technologies, service providers are adding more and more base stations to improve their service coverage and performance. Even with several advanced strides in the evolving technologies, still most of the voice, text, and basic data is based on relatively old GSM technology. And GSM was the beginning cellular technology, and they did not have any native security baked into it at the time of its early evolution. And unfortunately, a simple vulnerability in GSM protocol has paved the way for the popularity of these fake base stations. What this vulnerability means is that a base station can authenticate and authorize the use of phones, but there does not exist a method for users to authenticate the base station. So a user cannot distinguish if the phone is connected to a real base station or a fake base station. This vulnerability has paved the way for new crop of adversarial attacks on mobile users. These fake base stations spoof the wireless parameters and properties of a real base station and transmit at a very high signal strength, and it also thereby forces nearby users to detach from their existing base station and come and attach to these fake base stations. Once attached, these fake base stations can launch a variety of fraudulent activities to scam users by sending them phishing messages. These fake base stations are also used increasingly more and more by criminal gangs who end up using it for their own profit. This is a typical a design or a architecture of what a base station is out in the world. A legitimate base station here with its own big blue circle representing its coverage. You can see these real world users sort of representatively attached to this legitimate base station. Now enters the fake base station. A fake base station um, is a simple wireless transceiver whose transmission operation are completely controlled by the software running on an engineering laptop. And there are several implementations of these GSM technologies, and OpenSDR is one of them. And fake base station operator might also employ another engineering cell phone primarily to scan wherever they are launching this FBS to scan what other legitimate BS stations are in the nearby locality and either use those configuration as a part of the transmission that they are doing, or to use that configuration to not transmit those information so as to not collide and get detected by legitimate base stations. Here are two depictions of what a fake base station in real world would look like. As you can see, it's not very big. It's very small and they don't cost too much as well. They hardly run to probably $600, $700 and they can be set up in an afternoon. Um, Now let's see what a typical fake base station attack looks like. Here you see a current user who is connected to a base station which is transmitting at a signal strength of minus 70 dBm, and we have other two base stations which are relatively far away at minus 100 dBm, and one relatively close at minus 60 dBm. And this user has a current connection with the base station which is transmitting at minus 70 dBm. Now, when the fake base station operator wants to send SMS message to this particular user, the operator would first use an engineering cell phone to find what the closest legitimate base station is, and then get the frequency, base station ID, and signal strength information, which then the fake base station would use for its transmission purposes. The fake base station then starts broadcasting its system information and also sends a location update to this current user. The current user is now forced to reevaluate his selection criteria, and the user thinks that it might have to switch its base station connection because it's now in a new location. And its decision criteria is usually based on the signal strength. So looking at all these neighbor base stations, it finds the fake base station to be of the highest strength. The point to be noted here is the fake base station sometimes are transmitting at really unsafe levels of power. So now the user terminates its current connection with the legitimate base station and initiates a new connection with this fake base station. Terminates with the current connection and then establishes a new connection with the fake base station. Once a current connection or a connection is established with the fake base station, the user is completely at the whim of the operator of the fake base stations. So if a fake base station operator wants to send a SMS and make it look like it's legitimate, he can do so. So he can operate and send an SMS, say, let's say, send a scam message with some fake account number details. And once he realizes that he has achieved what he wants, he can then stealthily turn down his attenuate his signal strength, change his base station signal, and kind of go untraceable. There has been so much growing interest in curbing these fake base stations, both in research, academia, and also in practical real world scenarios. We'll go over some of the current methodologies. A static electronic fence can be deployed in any small geographical locations with what is called as a networked cellular sensors or low power signals, low power cell phones, which can sense the presence of a fake power base station. Though they are very effective, they are mostly a temporary solution, and they don't scale to larger geographies due to their huge infrastructure costs. Another interesting methodology is to retrofit patrol cars with FBS sensing sensors, and they can patrol around important geographical locations. However, this random walk approach is not very effective because the fake base station operators can sense the approaching patrol car and can turn off, and also this cannot be scaled for large geographical locations. Another possible solution is to allow users to actively report the presence of fake base stations either by their perceived sense of a scam SMS message or by fluctuating signal on their phones. However, this method is not very effective because most users don't even realize that there exists a fake base station and that they are attached to fake base stations. In academia, a few preliminary technologies have been recently proposed to detect and locate these FBSs by monitoring the base stations either on the client side or on the carrier side. Some of the popular ones are Snoop Snitch, Catcher Catcher, and Android MC Catcher Detector. All of these methods are either based on an Android app running on the client side, which does in-depth and fine-grained analysis of the cellular signals, checking for the base station consistency. All of this is done on the mobile side, or it also checks for irregularities at the carrier side. However, it is still questionable on how much effective they can be in the real world and how much they can be scaled. The proposed FBS radar system in this paper is conceptually similar to the client-side methods just mentioned here, but the difference is that it turns end-user devices into a crowdsourced network of sensors. And this FBS radar is being tested and to be scalable with currently about 100 million users, and is a generic implementation and is not relevant to what type of phone it is or what kind of a privilege you have a phone, and does not go into in-depth fine grain analysis on the mobile itself. Now let's delve into the system proposed in this paper for the FBS radar. Here we present the architectural overview of the FBS radar system. You can see the mobile user component generating the user report, which is sent to the cloud, and the cloud side implementation includes three functional components, including content-free analysis, content analysis, SVM machine learning cluster, along with four data components, including authoritative phone number list, base station location database, Wi-Fi location database, and the message logs. It's interesting to understand how the system is scalable because the paper actually works in collaboration with Baidu Phone Guard, where it taps into the customer base or the user base of this particular app, which scales for more than 100 million, which has currently more than 100 million subscribers. So a typical user report looks something like this, where it includes information from the base station that it was recently connected to, the time, the signal strength, and the base station ID, includes the sender's phone number, the content of the message, and also the neighboring Wi-Fi access stations MAC addresses. And all these user reports are generated every time a particular SMS is tagged as suspicious. And the paper defines a suspicious here as a message which arrives from a sender who's not in the recipient list, or a sender's number is not in an authoritative number. Then it is tagged as suspicious, and a user report of this format is generated. With user reports generated from 100 plus million users, are crowdsourced and sent to the cloud. The paper explores a variety of methods on how this data was used to detect or identify a fake base station. And of that, they identified five key methods, and some of them is what we'll be discussing. In method one, this is a method which is based on signal strength examination. The idea here is that fake base stations are assumed to be transmitting at very high signal strength, much powerful than minus 40 dBm. And if you look at the graph, we see the signal strength and the x-axis and CDF, which is like a perceived signal strength of the user. And if you can look at like minus 40, that is when the fake base messages are identified. Messages from fake base stations are identified. But this method may not be close to reality because even fake base station operators do not operate at such high power, which is very inefficient when they could actually get their work done when transmitting at something close to what a legitimate base station would transmit. So though that is the case, it still was able to used to identify about 0.23 percentage of suspicious messages that were actually being sent by the FBSs. In method 2, the base station ID is checked for the right syntax, and based on that, it would be the model would determine if the message is from the fake base station or a legitimate base station. But this method is not very effective and may not be close to reality because fake base station operators are really smart, and they very rarely would make mistakes when making such or construct such erroneous base station ID. However, in the 100 million plus user report that were generated, about 0.15 percentage of suspicious messages were found to be sent by base stations with syntactically invalid IDs. In method 3, message content mining, the paper explores the idea of using a machine learning technique, specifically a support vector mission, as a text classifier on a bag of words trained on a 200,000 labeled SMS messages. It is immediately clear that because the learning has to happen over the content of the messages, it clearly violates user privacy and is computationally intensive. It has multiple stages on how they go about, including labeling suspicious messages, word segmentation, extracting the feature, hand engineering the feature vectors, training it, pre-processing, and backtesting, and the final classification on the test set. Though it is computationally ineffective, it was found about 0.16 percentage of suspicious messages that came from authoritative numbers were determined to contain fraudulent text information. Method 4, called the base station Wi-Fi location analysis, is based on the user-generated report. The user-generated report includes the most recently connected base station ID, which actually can map to a fixed base station location generated from the carrier details, and also the Wi-Fi access point location that is part of the user management. The idea is that this base station location information and the user Wi-Fi location, they should be pretty close to each other and they cannot be far off. But from the data, it is understood that for fake base station, the distance between a legitimate base station location or the Wi-Fi location and the fake base station BS location, they are pretty far off. Now, this is a very effective method, and this is what the paper also says the most effective way of detecting the suspicious messages from the fake base stations. In fact, 4.1% of suspicious messages were sent by base stations that were not in their correct geolocation. That is, the base station or the fake base station was actually spoofing a legitimate but far off a distant base station. Now, the paper goes in detail on why such an effective method cannot be counterfeited or counteracted by the fake base station operator. The fake base station operator, it is very easy for him to change the base station or his base station ID to mimic something that is closer to the legitimate base station. But doing so would be counterproductive because um, the if a fake base station with a nearby legitimate base station ID sends a location update request, the uh, the user mobile is going to do a selection criteria and is going to think that the new location update that it is getting from the nearby base station, fake base station, is not too far off, and so there is no reason for the mobile user to move to a newer base station, and it might be happily, and it is okay for it to be happily connected to the existing base station. So it will actually be counterproductive for the FBS operator, and that is the main reason why this method is effective in identifying almost 4.1% of the suspicious messages. And then there is the method 5, called the base station handover speed estimation. This method is mostly a complementary of method 4, which is the most effective method of all the 5 methods. And the main purpose of this method 5 is a situation where a Wi-Fi location information is not available. We have the base station information from the last 3 base stations the user is connected to, but we do not have a clear Wi-Fi location or Wi-Fi location access point information. And this is primarily the reason why the user report contains a 3 base station information. Here we see the base station depiction of BS1, BS2, BS3, each radiating at a radius of R1, each given a parameter of T1, S1, ID1, each representing the time, signal strength, and base station ID respectively. So the idea here is to estimate the base station handover from this time and the signal information. Whenever a user moves from one base station location to another base station, there is a handover that happens, and this usually happens very pretty quickly. And when the user report is generated, we have this time information for each of the base station location and how long the user was in that base station. So with this, we'll be able to determine the handover speed estimation, a max estimate, average estimate, and the min estimate. When all these three max, min, and average estimate are subject to some conservative and moderate threshold, we would be able to determine if the messages are in fact from the fake base stations or the legitimate base station. And this is actually quite effective than the first 3 methods, with detection rate of about 0.39 percentage of suspicious messages were identified as coming from the FBSs. This method again is mostly a complementary of method 4. Let's now go over the deployment experience. As mentioned earlier, this paper implemented, not only designed, implemented, but also deployed this proposed method in real world by tapping into Baidu's phone guard app. Which consists of about 100 million users, and the deployment experience was also captured in this paper. Based on the five methods described earlier, more than 4.9% of suspicious messages were identified as coming from the fake base stations. The false positive rate is only 0.05%, and this is based on the user feedback, mainly due to the inaccuracy of our Wi-Fi database. When it talks about the user feedback, what it means is that whenever the system identifies that a particular suspicious message as to have originated from the fake base station, it communicates back to the user via the phone app and asks the phone user for a feedback if it indeed was a fake message or a scam message. And based on that information, we can see the false positive is only 0.05%. The other key aspect is that the set 3, which is actually the results from method 3, comprising from the message content mining, the machine learning method, whatever it identifies is actually already also identified by the rest of the four methods. So we can safely ignore method 3, and this actually is effective because there is no need to collect the text content of users messages, thereby being a little more ethical and not looking into or violating user privacy. So in addition to detection, this paper also recommends how fake base stations can be located, and this helps law enforcement officer to take down these fake base stations as possible. So this paper proposes a way of localizing these fake base stations to a particular location. So the idea is when multiple users are reporting fraudulent messages, there are user report generated from each of those users. So with that in the background, we employ a clustering algorithm which takes into consideration the base station ID, the time when it is happening, and also the um, location where it is happening from the Wi-Fi information. With this, they run an clustering algorithm, and based on the deviation distance, they determine the location of a fake base station. It is to be noted that this algorithm or this methodology is not very highly precise, but rather an estimate or an approximation that is still good enough for the law enforcement officers to track down and crack down on those fake base stations. In summary, this paper discusses a design, implementation, and improvement of a fake base station radar, which is a large-scale fake base station detection and a localization system. And this has been used out in the wild in the field with a subscriber base of over 92 million, and it has helped successfully quarantine millions of spam and fraudulent SMS messages every day, and it has also helped law enforcement people to harass hundreds of FBS operators. This FBS radar relies on the automated collection of suspicious SMS messages from end user devices to identify the fake base stations. And the paper evaluates five different methods that leverage this data to detect fake base station and find that the fake base stations can be identified with relatively high precision without needing to analyze the content of SMS messages. In the future, it may be possible to develop better algorithms with a higher recall by leveraging the data produced by this fake base station radar as a ground truth. Thanks for watching. Thank you.